Thank you for being patient. We had a very long lab. We'll try on Wednesday to go faster if we can. We'll see. All right, so let's continue where we left off last Friday with carbohydrates. I didn't get a chance to put a recap. Usually before lecture I run and do recap questions, but didn't get a chance to do that. So we only talked about general carbohydrate introduction. Is lignin a carbohydrate? No. Is it a dietary fiber? Yes. So lignin is not a carbohydrate. It is a dietary fiber. What's the definition of a dietary fiber? It wasn't in your notes, Kia? What's that? It cannot be digested. So dietary fiber is a portion of the food we eat that does not get digested, and usually it's from plant sources. Okay, let's see. So let's continue. All of what we covered on Friday were introduction to carbohydrates. So now let's talk about the actual analysis. And we always start with sample prep. Oftentimes, if the sample is high in moisture, we start with removing the moisture so that we have dried, and then we homogenize that sample. So we start with the dried and homogenized sample. If it's high in fat, before we do carbohydrate analysis, we extract the fat. So we can do that by batch extraction or by sock slits. So batch extraction, you can do that either with any organic solvent. Often it's done with hexane or a combination of ethyl ether and petroleum ether. Or you can run the sock slit like you did in the lab and defat the sample, get that sample that has been defatted, and continue with the carbohydrate analysis. So this is the assay that you're going to run in the lab, and this assay is done for either research purposes. That means when you have an isolated sample that is mostly carbohydrate, nothing much else is in it, or it can be for juices, and that's what you're going to do next week, where you're going to determine in beverages total carbohydrate, not necessarily juices, but beverages. So you'll have diet, is it 7-Up is what we do, 7-Up or Sprite? Yeah, we do 7-Up and beer, not for drinking, for measuring carbohydrate. So that's what you're going to do next week. And these beverages, there's not much in them other than sugars and alcohol, obviously, in the beer. So it's done for simple system where you don't have complex matrices. Okay, so with that, so you would analyze the total carbohydrates using a method we call phenol sulfuric acid method. So what happens there is you use a concentrated sulfuric acid. So again, the concentrated sulfuric acid is very powerful in breaking bonds. So it, first of all, it generates heat. So when you have your beverage and you add sulfuric acid to it, it will start digesting your carbohydrate and generate heat. The heat generated will also help in the conversion of the monosaccharides after breaking bonds. You end up with the individual units, monosaccharides. The heat that is generated due to the H2SO4 and the acid present will convert monosaccharides to furans, which basically you take the monosaccharides and it is an emulsation reaction, mostly dehydration. So you're losing of water and you generate different furans based on the structure and different components of the monosaccharides. So you have these furans now that are generated. Then you add your phenol. So this lab, Cindy calls the most dangerous lab. Yeah, it has the concentrated H2SO4 and then it has the phenol, which is toxic. So we have to be super careful next week in lab. So the furans will react with the phenol that we add, and then it will give you a colored substance, and that we will use a spectrophotometer to measure the absorption that is generally between 480 to 490 nanometer is the lambda max, which you will actually determine yourself. So you will be measuring at different lambdas or wavelength, and you're going to identify the lambda max yourself in the lab. So it's a good exercise. Well, because we are measuring based on absorption, in order to determine concentration, we have to plot standard curves. So you will be using glucose as a standard, and then you're going to prepare glucose at different concentrations and then plot the concentration versus the absorption to get your equation of the line and then determine the concentration of carbohydrate in your sample. So one important thing that I'd like to mention, that this reaction is not a stoichiometric reaction. That means it's not based on one-on-one interaction. It's mostly based on the structure. So fructose, for example, will give different intensity in absorption than glucose when it reacts with your phenol. So that's why the standard curve is very important, and what you use as standard is very important. So oftentimes, if you know the expected composition of your sample, you construct a standard containing those different monomers in your standard. So combination of fructose and glucose, or a combination of whatever you have in your sample, you try to formulate that standard to take into account that it's not a stoichiometric reaction. So the standard that you use is very important in this assay. So again, this assay cannot be applied to any food matrix. It's not used for labeling, for your food label or nutrition label, just because food matrices can be complex and there are a lot of interference in there, so you cannot use that method to determine total carbohydrate in any system. It has to be a clear system that does not interfere in the absorption measurements. That's key. That's why it's mostly used for research. We actually use it in the lab quite a bit when we collect fractions out of our column to determine how much carbohydrate is still remaining in our fraction when we're purifying different components in the sample. So it's a used method, but it's not very useful to determine total carbohydrate in a complex food matrix. Okay, so you'll be doing that in beverages next week. So moving on, carbohydrates, like I said last week, they're very complex and they're made up of different components. They can be monosaccharides, disaccharides, oligosaccharides, starches, fibers. There's so many different components that can be under the category of carbohydrates. So what we're going to do now is talk about methods to analyze the small sugars and then methods to analyze starch and fiber. So small sugars, then starch and fiber. This is how we're doing it. So we'll start off first with the small sugars, mono-di-oligosaccharides. Excuse me. So we will cover colorimetric methods that are mostly based on the reduction capability of the sugars. So it's mostly for reducing sugars. And then we'll talk about chromatographic methods. So you will bring back your chromatography knowledge for this application here. And then enzymatic methods. Okay, so in order to determine the small sugar components or the concentration of small sugars in my sample, I need to purify them, extract them from the matrix. So like I said earlier, we start with drying if we need to dry the sample. Then defatting, okay? So I'm done with moisture, I got rid of moisture, I got rid of fat. What's left in my sample normally would be carbohydrates, potentially starch, fiber, proteins. I don't want those. Okay, I don't want starch. I'm after monodi or oligosaccharides. So I need to get rid of these other components. So in order to do that, I can isolate, there's one way, solvent extraction, isolate my small sugars from the complex matrix. So in order to do that, I can solubilize in 80% ethanol. So it's alcohol solubilization, warm 80% ethanol. So that means I can put my sample, let me see here. Okay, so I can put my sample in a beaker, potentially, and or not necessarily a beaker, in a water bath here, it seems like, on a hot plate. And then my sample is in this round flask with ethanol, 80% ethanol. I have a distillation unit here. So what happens here is reflux. So I can benefit from having a distillation unit so that when my solvent evaporates, it goes back down into my sample. So it can be more efficient rather than heating it and losing the solvent. I want to keep the solvent in, so it would be best to do it under reflux conditions. So that means closed system with a distillation unit. So then my sample is in here with proteins and fiber and carbohydrates, and then my small sugars. So my small sugars will be soluble in ethanol, while everything else will precipitate. So large polysaccharides and proteins are insoluble in 80% ethanol. So I will just take the ethanol with the sugars after an hour or two of refluxing, and now I want to remove everything else that is not sugar in there. So what I do is, first of all, I will evaporate the ethanol by rotovap. All of you have seen rotovap already when you did the isoflavone extraction. So it's basically you have you evaporate under vacuum to enhance the evaporation process at lower temperature. So you get rid of the ethanol, and then you will have your extract in that original flask. But you might get small components in there that you are not interested in, like organic acids or flavors or amino acids. These are all charged, whereas your sugars are not charged. So in order to get rid of those that you don't care for, you're not analyzing for amino acids, you're not analyzing for organic acid, you can run your sample through ion exchange cartridge. So then all of your charged components will be left on the cartridge, on the ion exchange resin, whereas your sugars will dilute with the water. And then now you have a solution of your sugars, which you can analyze using the different methods I'll talk about later. So this is the first step, is extracting them, having them in one solution mixed. So now you have whatever you have, glucose, sucrose, raffinose, tachyose, all of these small sugars, you can have them in one solution to analyze. Another treatment, in order different than solvent extraction, is the Caras treatment. Here you use a reagent called as Caras reagent, composed of potassium hexacyanoferrate and zinc sulfate. So this type of reagent breaks emulsion and precipitates proteins and polysaccharides. So you end up getting rid of those, and what remains in solution are your small sugars. So that is another way of extracting your small sugars. Okay, so now you extracted your small sugars, and now we want to analyze them. The first category is your calorimetric methods. And mostly the calorimetric methods are used for reducing sugars. So these methods are based on the reducing capability of these sugars, and your reagents have cupric ion in them, an alkaline solution, and cupric ion. So the cupric ion is reduced by the sugar to cuprous, and you form cuprous oxide usually, and it's a red precipitate. And then you can measure that red precipitate either gravimetrically by weighing it, or by titration, or by spectrophotometry, actually. So you have, again, the reaction. It is blue. Your solution or reagent is blue because of cupric ion. And then when you have a reducing sugar in the presence of cupric ion, it will reduce the cupric to cuprous, and you get cuprous oxide as a red precipitate. So you end up with something like that. You can end up with something completely dark like this. What do you think happened here? Very simple. Simple thing that you deal with all the time when you are measuring constituents. Why do you have that much dark color? Simple. Very, very simple. Yes, Anna?
Yeah, like other components in it besides sugar?
You could have other reducing agent. Yes, that's very true. That is one. But there's something else that is even simpler than that. That you usually have to take into account every time you're preparing a sample, you do something before you measure. You've done that so far in a couple of labs.
Is it just dirty glassware?
Not quite. We do clean our glasswares. You are being creative, but good creativity. But that is not what's happening here, Sophie.
Too much sample?
Yes, we dilute our samples. You always dilute your samples. So your sample is concentrated. Okay, you have lots of reducing sugar. You end up with this. You cannot separate it from the rest of the reagent. You cannot see it precipitate, basically. So what we do is we always dilute so that our reaction works and we can get good determination. We dilute and then we convert back by taking into account the dilution factor. So very simple. Okay, so the three methods that are often used are Lane-Eon, Smoogie-Nelson, and Munson-Walker. They're all named after the people that created them. But the most common one is Smoogie-Nelson. But all of them, again, all of them have cupric ion, has the alkaline condition, and then different reagents are used, okay? So I don't want you to learn these, to know them, but know that these methods differ in the reagents. What I want you to know is quantification can be either by gravimetric, weighing the precipitate, or titration by sodium thiosulfate or potassium permanganate, or spectrophotometric assay when we have an arsenomolybdate reagent, which is blue in color, that gets reduced it has cupric, gets reduced by the sugar and gives you another color to be absorbed at 520. Okay. So colorimetric methods are for reducing sugars, but we can analyze other sugars, can we? Can we not analyze sucrose? Is sucrose a reducing sugar? Huh? It's not. What do we do in order to use these colorimetric methods? Can we do anything to the sucrose? No? It's not reducing. What is sucrose made up of? Glucose and fructose, right? Are they individually reducing sugars? Yeah, they are. So
Or hit it with an acid.
yeah, hit it with an acid. So you digest the sample with an acid, with a little bit of heat, you break that glycosidic bond. So when you break the glycosidic bond, you release glucose and fructose, and you can use these methods to determine the concentration. enzymatic method. This enzymatic assays are very common in food analysis. We have a chapter after carbohydrate on use of enzymes in food analysis. They're very common. Enzymes are biological catalysts. They're used to speed up the reaction or initiate a reaction that would otherwise require a lot of energy, so it will reduce the activation energy. And it's very commonly used in carbohydrate analysis for monomers, for dimers or disaccharides, oligosaccharides, and also for starch and fiber. We rely on enzymes there. It's mostly specific to the substrate of interest, and yeah, it's mostly specific for the substrate of interest. So your enzyme should react with the substrate in order to produce a product. And we'll talk more about this when we cover enzymes in food analysis. But it's used to determine constituents, which are usually substrates for the enzymes. And the whole reaction or the whole assay is based on spectrophotometric analysis. So we're either determining the absorption of the substrate or we're determining the absorption of the product. If we're determining the absorption of the substrate, as it gets consumed by the enzyme, absorption will decrease. If we're determining the absorption of a product, as the enzyme works on the substrate, the absorption will increase. So it can be an upward curve or a downward curve of calibration curve based on the concentration. Oftentimes we have a coupled reaction. That means you need two enzymes to get you to quantitate. So we call this coupled because the first reaction gives you a product. None of these reactant or products absorb light. Okay, so we're stuck. We did not get to something that is measurable. But we need the product to get me to a second reaction, upon which the second reactant here, C, or product, R or S, will absorb light. So then I can measure. Then I can take a measurement with the second reaction. So the first reaction is auxiliary reaction. The second reaction is my indicator reaction. The reaction that gives me the absorption that I'm looking for. Auxiliary reaction is also known as the measuring reaction. So good for you to know these terms. They can be used exchangeably. Okay, so here's an example. So let's say I'm measuring glucose. So there are different ways of measuring glucose. This is one of them. So in this case, I'm using, again, a coupled reaction that requires two enzymes. The first enzyme is hexokinase. The second enzyme is glucose 6-phosphate dehydrogenase, losing a hydrogen. Okay? So the first reaction, I need ATP as a reactant. So glucose ATP in the presence of hexokinase will give me glucose 6-phosphate and ADP. So one phosphate from ATP was gained by glucose at the 6th position. So glucose 6-phosphate. All right, so now none of these absorb light. Okay, so now I need my second reaction. So glucose 6-phosphate with NADP, another reactant. Okay, NADP does not absorb light. This does not absorb light. In the presence of glucose 6-phosphate dehydrogenase, so I'm losing a hydrogen. I get 6-phosphogluconate. I get NADPH, so NADP gained the hydrogen. This one lost the hydrogen. So this product right here absorbs light. So here it is. It absorbs light. Lambda max is around 340 or something. So you measure the absorption of NADPH, and then you back calculate the concentration of glucose based on the molar ratio within the reaction. Okay, pretty simple. So for carbohydrates, it is applied for so many different substrates or constituents. You have specific enzymes for fructose, glucose, galactose, for also lactose, maltose, or sucrose. You can measure them via enzymes. Polysaccharides, you can measure amylose, amylopectin as well, and we'll talk about that later when we talk about starch determination. So many advantages. It is specific for substrate. So if you're after glucose, often you are measuring glucose. Kits are commercially available. Megazyme, Novozyme, Sigma, they all sell kits. And it's pretty straightforward. You get the kit, it has all the reagents in it, the enzyme, everything you need. You just have your sample to dilute and run. Generally have low detection limit, low threshold, so very sensitive. In terms of disadvantage, since it is based on spectrometric analysis, so that if you have any compounds that might absorb at the same wavelength, then that might cause interference. Not always 100% specific, and that is not because they're not specific to the substrate themselves. Sometimes the enzymes are not 100% pure. So you might have other enzymes in the mix that might work on other substrates, just because of the purity of the enzymes that you obtain. Okay. Moving on to your favorite subject, chromatography. How did I guess that it's your favorite subject? Am I fooling myself? Rachel thinks I'm fooling myself. Is she right? Yeah? I like to do that. Okay. So paper and thin layer chromatography, they are used but not very much. They're mostly qualitative. You can do quantitation, but it's tedious if you want to do quantitation. You either have to run a standard on the same paper or thin layer chromatography plate, and then measure intensity of them based on the standards you run, or scrap off that spot and analyze it again, which is tedious, so it's not very much used. This is just an example application. If you use paper chromatography, you can use cellulose filter as a stationary phase, and then as a mobile phase, you can use propanol ethyl acetate plus water. So if I ask you in a test, give me an example of paper chromatography for mono and disaccharides, here you go. Give me an example of thin layer chromatography. You can use cellulose, silica, or impregnated silica. Mobile phase, similar to paper chromatography. It's an organic phase. So that means, okay, refresher. If you have an organic mobile phase and a polar stationary phase, this means it's normal phase or reverse phase chromatography. Raise your hand. Normal phase chromatography. See, you have to remember chromatography throughout the semester. Till the very end. It's going to haunt you till the end. So remember that. It's normal phase chromatography. And compare TLC compared to paper chromatography, you have enhanced separation, resolution, spots are sharper. So there you go. Okay, let's go to the real deal. The real deal is these chromatographic methods that are HPLC-based, high-performance liquid chromatography. They are very commonly used for small sugars analysis. Okay, so all of these wonderful chromatography that you learned about, we're going to look at applications now. So normal phase chromatography, reverse phase, ion exchange can be anion and cation. Are sugars, do sugars carry charge? No, they don't carry charge. Yet we can still use ion exchange chromatography. How? We'll talk about that. Okay, so normal phase. Refresher again, your normal phase, stationary phase is polar. So you can use unmodified silica. But unmodified silica bonds really strongly with the hydroxyl groups of the carbohydrates. You can barely get separation if you use just unmodified silica. It's almost impossible. So what do? We use a modified silica, and we call this hydrophilic interaction liquid chromatography. Okay. So what's the chemically bond silica that we can use? The most common one is the amine bonded stationary phase. So basically you have your silica bonded at the end with an amine group right there. Okay. So this amine group reacts via hydrogen bond with the hydroxyl groups of your carbohydrates. Okay. Since it is a normal phase, your mobile phase is mostly nonpolar. It starts with 50 to 85 acetonitrile, and then you decrease your acetonitrile concentration over time. If depending on the detector that you're using, and I'll get to that in a minute. Sometimes you cannot change the concentration of your mobile phase. You have to go with a isocratic mode of separation. So separation can be influenced by column temperature, and oftentimes separation is happening when you put your column in an oven to control and enhance the separation. So before you look ahead on the next slide, if we have separation is based on hydrogen bonding between amine groups and hydroxyl groups. If you have glucose and sucrose, which one will elute first? Do not look ahead. Somebody is smiling. Do not look ahead. Just think about it. So reaction is with the hydroxyl groups. What? You're tired, I know, but it's very simple. So which one has more hydroxyl groups, glucose or sucrose? Why would glucose have more hydroxyl groups than sucrose? Huh? Seems like it would. I like your answer. But glucose is one. And then with the sucrose, you have fructose, and it has more hydroxyl groups. So you have hydroxyl groups of glucose and hydroxyl groups of fructose. So which will elute first? Did you eat? Did you guys eat? Some of you says no. Sucrose will elute first? Will? Yeah? Are you gonna sing it for me?
Sucrose will elute first. That's all I can.
That is completely wrong. No, the more interaction with the column, it gets delayed. So the more hydroxyl groups you have, the more it's going to interact with the amine groups in the column. It will take longer to elute than a compound that has less hydroxyl groups will interact. Less with the amine groups will elute first. What? When you have more hydroxyl groups, they will have more groups to interact with the column. And the more interaction of the column, they will be delayed. With the less hydroxyl group, they will interact less with the column, they will come out first. Yes?
I just want a clarification.
Yes.
The column has amine groups on it?
Yes.
Okay.
And the amine group interact via hydrogen bond with the hydroxyl group. So the nitrogen is an electronegative atom, right? So the nitrogen will interact with the hydrogen from the hydroxyl group via hydrogen bond. Okay. So fructose, glucose, saccharose, lactose, and it's all based on the hydroxyls and the availability and the positions of the hydroxyls available to interact with the column. All right, so detection is usually with refractive index detection. So in this particular case, gradient elution is not possible. Do you remember why? with refractive index. You cannot change the concentration of the mobile phase. You remember why?
Because as you change the concentration, it will refractive.
Yeah, because refractive index by definition is impacted by whatever concentration you have. It's not specific. If you change the concentration of anything, any solids, you're going to change the refractive index. So if we're after carbohydrates, specifically, in your sample is nothing else, you need to keep the mobile phase constant. Okay. Oh, so sad. Time is up.